solving now for case number 2, where we're going to use this equation, and the mass 2 is inside of mass 1. Again, center to center, center of mass to center mass distance is r. It's now this equation. We're going to use a very similar procedure. Essentially, the system is identical. The forces, the directionality, the forces, the directionality of the change in the radial this distance between the two parts is the same. We know, again, we're going to have a positive work coming out. So let's just get started. So the internal work is the integral of the force dot the change in displacement. So putting in the force value right here, we can solve it. These are all constant terms, bringing it outside the integral. And so we can, this is a function of r. So the integral of that gives us r squared over 2. So this is our relationship for internal work. Once again, we know that change in gravitational potential energy is minus the work internal. Taking the indefinite integral, I get this equation with respect to r squared plus some constant. So we have now two equations for gravitational potential energy, one outside and one inside. Those two values should be the same in the case where I'm right at this edge right here, transitioning between inside and outside the object. So when little r equals big R, these gravitational potentials are the same. So I could take this value right here, substitute in big R for r squared. That ends up with 2 over this term over 2r plus the constant, and I have this term right here where r is big R is big R. So I can put that there. Here's my equation. Just gonna solve for constant. Bring this term over to here, and there's my constant term. So now I know my constant term here. So now for the complete form of the internal gravitational potential energy, I have this term minus plus the constant, which is this minus term right here. Now graphing it, let's graph potential energy as a function of r. From the first equation, we know at r is big R right at the surface right here. This was my term for my gravitational potential energy right here, and then I have this form of the equation, which goes to potential energy is 0 at r is infinity. Again, I match right here at that point, and using my second equation right here, I get right here is this constant. So when r is 0, I just have this constant term. So it's 1.5 times the value here at the surface, and then you can see this gravitational potential energy is a function of r squared. So, and since it's just like an ideal spring, you get this form. So essentially, and you could consider it, if I even went in this opposite direction, it would have the mirror image of this. If I put a part off to a little bit off to the end, so I put it in the middle, there's no reason for it to move anywhere. I've displaced it a little bit off to the side inside the part, and I let go of it, it's just going to be like a spring going back and forth inside the body. Another way to think about it is, so we know that work, the force is minus the derivative of potential energy with respect to the radius. So that's just the slope of this. So at this point here in the center of the body, my slope is 0, so I have no force. And so slope anywhere here is going to tell me what the force is at this force right here. And so you're going to see that we're going to have the highest slope right here at r. So then, considering it further, we can look at, so from potential energy, the derivative of the potential energy is my force. Oppositely, we know that work is the integral of f dot dr, and talked about internal energy minus the internal work. So we know that if I plot force, that's going to be the derivative of the potential energy, as we saw here before. So if I go to my force equations, so this is my force inside the part. It's a linear function of r up to r. Okay, and then I have this force value when r goes big R internally, and then outside force is this relationship. It's related to some constant over r squared. And so there's my force relationship, which is the same kind of information I can get from the slope right here. Work is the integral of this radial force dot radial displacement, and change in potential energy is minus that integral. So if I have any change from radius 1 to radius initial to radius final, so we'll call that radius initial to radius final, this area under that curve, the integral, minus that integral is a change in the potential energy. So this minus area is a positive value. So going from radial position 1 to radial initial or radial position final, would going from here to here. So that magnitude of change in potential energy is just this area under that curve. And I could continue doing that and find the change in the potential energy is just area anywhere along this curve. And inside the body, you can see the force is proportional to the radius. So it's right here. So that's again a constant. So that again is acting like a spring. So that it would have this force like this, and it would have the squared function for the potential energy. This was a good illustrative problem showing that for potential energy for work and force, that they're related to changes in position. Contrarily, we learned in the previous video that change in momentum, force, and time are related in a similar manner. This graph also shows that if I had the object at the surface and at the surface of R, I would need this level of positive kinetic energy for the system to be unbounded, for the masses to essentially be able to get totally away from each other, as opposed to I need 50% more kinetic energy if mass 2 starts in the center of mass 1.